Okay, guys, we're moving on to part 3, not part 2, like I just said, of this video here from section 1.1, and we're kind of moving into more of the 11.1 idea right now. And the main idea we're going to talk about here within section 11.1 is something important right here that is really kind of cool, I think anyway, and it's called Euler's theorem. Now, a lot of people want to mispronounce this guy's name and say Euler, which is kind of how it looks, but it's pronounced Euler. The guy was Leonhard Euler. He was a Swiss mathematician, and you'll learn more about him next year when you get into Algebra 2 and you learn about something called Euler's number, which is kind of like pi. It's an irrational number that goes on forever and ever and ever and never ends and never repeats, and has a lot of applications in growth models, money, things like that nature. So Euler's number you're going to learn next year is about 2.718, but that's not really relevant right now. Euler's theorem here, as it relates to polyhedra, says the following, that for every polyhedron that you can draw, the number of faces plus the number of vertices is always going to be equal to the number of edges plus 2. And this works in any of the figures that we've talked about so far. So let's go back and talk about what's going on right here. We're going to try to verify Euler's theorem for the following figure. Now, the first thing we should probably try to do is identify what type of figure it is that we're dealing with, although truthfully, this isn't all that relevant to being able to use his theorem right here. But what we see here is that we've got a polygon base on the bottom of this figure. As I look at it, it appears to have 6 sides, which makes it a hexagon, and then it looks like there's a congruent and parallel polygon base up here on the top. That makes this figure a prism, because it has congruent and parallel polygon bases on opposite sides of the figure, and connected by rectangles. That's the definition of a prism. When we try to describe a prism, we usually put the adjective in front of it, and that adjective tells us what shape the base is. We were dealing with hexagons for our bases right here, so we would call this particular figure here a hexagonal prism. Hexagonal prism. Okay, so to verify Euler's theorem, let's go ahead and write down what that formula was one more time. All right, so it is going to be F plus V is equal to E plus 2. All right, and if we were in a traditional setting, I would tell you guys, hey, we got to come up with a silly mnemonic device to be able to remember what order that's in. But for now, you guys are going to have this handy right here. So the first thing we probably better do is come up with a count of each one of those things. And again, trying to be systematic about this, let's think about F, the number of faces. Every prism is going to have 2 bases. And in this particular case, you've got a hexagon up here on the top and a hexagon down here on the bottom. So we have 2 hexagons. And every prism is connected around the sides by rectangles. And the question then is simply, how many rectangles are we dealing with? Well, with hexagons on the base, there are going to be 6 rectangles connecting the bottom to the top. So in terms of the number of faces, we have 2 hexagonal bases and then 6 rectangles. So the 2 hexagons, the 6 rectangles means that we're dealing with 8 faces in this particular figure. Let's switch to red now and let's talk about vertices. Vertices, if you recall, are the points where 2 different line segments come together. So let's start down on the bottom. A hexagon has 6 sides, and of course that means that it has 6 vertices as well. So we've got 6 vertices down on the bottom base. Up there on the top, we have vertices in the exact same 6 positions here. And there are no vertices in the middle of this figure. So 6 on the bottom, 6 on the top. That tells us then that we're dealing with a grand total of 12 vertices in this particular figure. Okay, now moving on to edges right here, and again, you can spend a long time here if you're not systematic about it. Let's think about the bottom. The bottom is a hexagon. It has 1, 2, 3, 4, 5, and 6 edges right there. The top is a hexagon. 1, 2, 3, 4, 5, 6 edges right there, and connecting the top and the bottom. 1, 2, 3, 4, and then on the back of the figure, 5 and 6 edges connecting it there. So 6 on the bottom, 6 on the top, and 6 connecting the bottom and the top means we're dealing with a grand total of 18 edges in this particular figure, and we always add a 2 at the end of that. And when they say verify, we're just supposed to write this out and then make sure we get a statement that is true. So let's go ahead and simplify the left side. The 8 plus 12, hopefully we don't need a calculator for this, guys, is going to get us 20. And on the right side, the 18 plus 2 is going to get us 20 as well. So sure enough there, we have verified Euler's theorem for this particular hexagonal prism. All right, that one worked out just fine. And we're going to do one more here before we're done. And on this one, I'm not going to give you the diagram. Let's see if we can't think about this one a little bit more analytically. Here we're going to verify Euler's theorem, for a decagonal pyramid. Now, I'm not even going to draw that one for you guys. I want to go ahead and think about this a little bit more analytically here. And my hope would be that you guys are now capable of the type of abstract thought that's going to allow us to envision this figure and figure out the number of faces and vertices and edges without having to draw it all out. So what we want to do here, without drawing it, is to think about what this figure looks like. First and foremost, it's a pyramid. And if we think back to what we did in some earlier sections, a pyramid always has one base, and we usually like to think of it located on the bottom of the figure, but it doesn't have to be. But for our purposes, sure, let's go ahead and think about that. So it's got one face down on the bottom, the base right here, and the name of the pyramid, in this case a decagonal pyramid, that tells you the shape of that base. So this pyramid has one base, and that base is a decagon. So in terms of counting the number of faces, we have one base down on the bottom, and then every pyramid goes up to a point up on the top, a peak, and those sides are always going to be triangles. So the question now is, how many triangles do we have going from the base, should be down here somewhere, and like I said, I'm not going to draw the whole thing, but going up to the top then? Well, every side of your base gets a triangle sticking out of it. A decagon, if you remember the DEC right there, a decagon has 10 sides, which means there are going to be 10 triangles going from the base on the bottom up to the peak on the top. So we know it now. The total number of faces, there's one decagon on the bottom, there's 10 triangles going up to the top. That makes a total of 11 faces in this decagonal pyramid. Okay, let's think about vertices. Remember, a vertex is a point, anywhere two different line segments come together. So again, let's be systematic about it. Down on the bottom, we have one base, and that base is a decagon. A decagon has 10 sides, which means it also has 10 vertices. So 10 vertices down there on the bottom. And in a pyramid, they all come from the base up to one single point up at the very top, or the peak or the vertex of that pyramid. So for the number of vertices, 10 of them are on the table, if you will. They're on the bottom, and one up on the top means that we have 11 vertices here as well. Okay, number of edges. All right, trying to envision this thing now. We've got a decagon on the bottom. That's 10 sides. That means that we have 10 edges down on the bottom. And then there are also edges connecting the base of that pyramid up to the very peak of the pyramid itself. And there's 10 edges then going from the bottom up to the top. So a total of 10 edges make up the decagon on the bottom, and another 10 connect that decagon up to the peak of the pyramid. 10 and 10 means that we're going to get 20 edges in this figure total. And then we're always going to add a 2 at the end of all that. And sure enough, the 11 plus 11 on the left is 22. The 20 plus 2 on the right is 22 as well. So there you go. We have verified Euler's theorem for that decagonal pyramid. You're certainly welcome to try to draw that out if you want. But I'm really hoping that at this point you guys might be able to kind of visualize that systematically and not have to take the time to draw it out. Okay, so that is the end of our 1.1 and 11.1 part 3 notes, and hopefully now we can start that worksheet for homework, most of which deals with this concept right here of dealing with Euler's theorem. Okay, good luck everybody.